All right. So today we're going to continue talking about relational algebra, in particular making queries with relational algebra. Now here, a query just means a sequence of operations on relations that result in one relation. And whatever relation you end up with, that's the result of the query. So a query here is really just a lot of manipulative steps to get from the relations some end relation that, you start off with lots of little relations, and then you start to combine them together if you like. You can union them, you can intersect them, you can multiply them, and sort of mix together the information that these different relations have. And then after you have a good mix and you know that everything that you want is there, then you can start trimming and start eliminating stuff that you don't care about so much. And then that's basically what you return. So that's what the result of a query is. Now there's a lot of overlap between a relation and a set. I think it's useful to have both in your mind. A relation is like a table with named columns. Each column also has a type, and then the rows of this table are the values for that row. And every row is one unit of, like, one packet of information. The other way that you can view this is as a set. This is a set of vectors, if you like. So here, the employees relation can be thought of as a set of size 3. There's 3 elements to this set. 3 elements or 3 vectors. Each of these vectors are 3-dimensional. The first dimension is social security number, the second dimension is name, the third dimension is lot. And so any point in this 3-dimensional space is going to have some social security number, some name, and going to be in some parking lot. And that will uniquely identify this vector in this case, 3-dimensional space. But if you have 10 columns, then you can imagine it as 10-dimensional space, and each of these vectors is an element of a set. And that set is just all of the points in that relation. And now that you have these sets, you can just do set operations on them. So intersections, multiplications, this kind of thing. Okay. So as far as the operations, these are operations done on relations. So this is an algebra of relations. You have 2 relations. In what ways are you allowed to manipulate them together? Here you can union them. You can look at their intersection. You can look at the set difference between them. You can cross multiply them with the cross product. You can project them. So that is eliminating one dimension, or many dimensions, or deleting entire columns of the relation. There's select. Select goes row by row of the relation and applies a predicate, a true-false statement. So from the first row, it applies this predicate, sees, is this true or false? If it's true, keep it. Check the next row. Is this statement true or false? If it's false, delete it. Okay, now go down to the next row. And that's what the select does, row by row. It has one statement, a true-false statement. It sees if this row passes or fails, keeps it if it passes, deletes it if it fails. And that's the select. From the set image of this, if you imagine a relation, instead of being a table, being a set of points in whatever dimensional space, then the select is looking at all of the points and picking out the points that work, or removing the points that don't work, however way you want to look at it. And then whatever set remains is the result. And then there's a rename operation, and this just renames a column or renames one of the dimensions. This is more for like bookkeeping. Okay. So those are all of our operations, and a query is given a bunch of relations. You want one relation that satisfies this query. One such query, here's 4 different relations. In this case, we only need to use 2 of them. Find all restaurants frequented by at least one person under the age of 18. So there's 2 relations that are relevant here, the person and the frequents relation. Person is relevant because that has the name and the age. And frequents is necessary because that has the names and the restaurants. And so in order to take these 2 relations and kind of smush them together into one, you cross multiply them. Now this big relation has far too many rows. It's sort of polluted. It has all of the information that you want, but it has too much stuff. It has stuff you don't care about. So then you go through the select and delete the rows or remove the bad elements of the set. And then you project, because you don't care about, in this case, the 5-dimensional vector of name, age, gender, name to restaurant. You just care about the names or the names of the restaurants. So you just return the restaurant column of this relation. Or you project all of these vectors down to a 1-dimensional space of restaurant. Okay. Here is a very similar type of query. Find the names of all females who eat either yogurt or salad or both. The main difference of this query versus the last one is the introduction of this or symbol. That, basically just expanding on the fact that that's a predicate. Yeah, you can have some things here. Oh, sure. I see a question about how a left or a right join would work through relational algebra. Sure, I'll make time for that next class, because there's stuff I want to get through here today. Yeah, good question, though. I'll do that. Maybe I'll do the left join, and then I'll ask other people to figure out how to do the right join, or something like that, instead of just doing both. I'm assuming that, if they're going to be like symmetrical. So, all right. Okay, now here, yes, okay, this is where we left off. Find the names of all females who eat both yogurt and salad. So as the previous query, we wanted results for either or. They eat salad or they eat yogurt or both. In this case, we want them to be exclusively salad and yogurt eaters. So one way to do this is to cross-multiply more. So first of all, you need to mix, if you like, the person relation and the eats relation, because the person relation has names and genders, and the eats relation relates names to the foods that they eat. So you need both of those. That's for the information part of it. Now, if you cross multiply that again with the eats, then that will allow you to write a select in this way, where you can check two different values of foods, because in this one column of eats, you can't check for more than one value. And this is going to be something that will come up again. The select has no memory, okay? So every time the select, the way it works is it looks at each individual row, or it looks at each individual point, and it decides, does this point fit my true-false statement or not? If it doesn't, throw it out. And now you have amnesia and you forgot about all of that. You just know the remaining points that you haven't looked at yet. Which is to say that if, because here, if we tried to do this without this third one, then when we're checking here, we can see that Amy eats salad, but we would say that that does not equal yogurt. So we'd throw it out. And then the next one, we'd see that she eats yogurt, but we don't remember the one that we just looked at that said that Amy eats salad. That's gone. We don't have any memory. We can only look at this one individual row. So, right. So that's one way to do it. You can cross-multiply eats with itself and multiply that again by person. That way you have all of the information. And by cross-multiplying eats twice, you're allowed to make this part of the query, or part of the select statement. So, and then you project. Okay. So that is one way of doing it. I asked at the end of last class if there was, if anybody could come up with a way, a different way of doing this, only using 2 cross multiplications, not 3. Did anybody come up with anything? Did anybody try? You're kind of lost. Okay, can you unmute yourself, Justin? Because that's great. If you're lost, stop me, because we're only going to be going deeper. So great. Which part, Justin?
I guess on how to get it down from 3 to 2.
Okay. But are you following all of the other queries so far? So we've seen three queries. Here's one, finding all restaurants. Here's another, people who eat yogurt or salad, and this one. So far, do you understand each of these?
Not great, no.
Not great. Okay. Okay, good. Let's go back to this one. Justin, if you could hang on here. We'll walk through this one, the either or. First of all, with these relations and this query in English, can you tell me which names should be the answer?
Amy and Jane.
Amy and Jane. Great. Yeah. So this should result with a relation that will look like this. Name. That's going to be in text, and there will be one row for Amy and another row for Jane. So this is should return that relation. Okay, great. And you had to look at these two relations in order to come up with that answer, right?
Yep.
Okay. So then for this query here, what does this do? We'll go inside out, which is generally the way to think about these queries, I think. This thing in yellow.
Is that where you do the cross multiplication?
Mm-hmm.
So, what is the symbol after the multiplication sign before the eats?
Yeah, sorry, that's a row. And that's a rename operation. So here we have sigma, S sigma for select. Here, for a rename operation, it uses the Greek letter R, which is a row. You can also just call it R if you like, or this P, pi, for project. So the first letters are supposed to be the same. That's why they're chosen.
So would that be saying that you're renaming the eats table and cross multiplying it with persons to add that in?
Yeah, except this doesn't rename the table. This renames a row, or a column, excuse me. It renames a column name. So here, the eats relation here, it has a column name and a column food. The
Yep.
rename operation is just going to rename that to look like that.
So I'm confused. It's going to rename it to look like what?
Like, okay, so we're working with these two relations, right? Eats and person. Okay, now we're gonna cross multiply them, right?
Yep.
But we are cross multiplying not person with eats, but person with row applied to eats. So what that row is going to do is change the name of this column to food 2.
Okay.
Oh, I'm sorry, to name 2. Name 2. From name to name 2. Okay, now these are the two relations that we cross multiply.
Yep.
Okay, and so what would the first row of this look like when you cross multiply these two relations?
Would it be name 1 from the person table? Or
Name 1.
are we only dealing with the eats table?
Well, I mean, it's both.
I know you're cross multiplying, but like when it returns, what table is it? Is it a whole new table
Yeah,
that
a whole new
has
table.
age and gender in it as well, or is it only the relevant information like name and food?
No, it has all of them.
Okay, so it'd be name, age, gender, name 2, food.
Yep. Yes. So this will result in a new relation that has name, age, gender, name 2, food. And so that's going to be one relation now. And that's why we renamed it. So this way these two columns can have different names. That's the reason for the renaming. Otherwise you'll have
And
two
then
columns with the same name.
what does this select outside that cross multiplication do?
So we'll get there in a minute. But first, what would be the first row here? Like what would be the entry there?
John, Peter, Amy, Jane? Or would it just be John, Amy, Jane?
Give me the whole row. So just whatever this Yeah, this row.
Row, not the column. Oh, John 16, male, John yogurt.
Yep. John 16, male. Okay, and the next one?
Peter 19, male, Amy salad.
Okay.
And then Amy 25, female, Amy yogurt.
Okay.
And Jane 23, female, Jane salad.
Okay, any more?
I don't think so.
Yeah, so the cross multiply, it doesn't multiply just the first row with the first row. It also pairs the first row here with the second row.
And then with the third row and the
And
fourth
then with
row.
the third row, and then with the fourth row.
Okay.
And the same thing when you pair Peter. Peter doesn't just get paired with the second row, it also gets paired with these others. Okay?
So you're going to have 16 rows then?
That's right. Yep, exactly.
Okay.
So down here is, oh, I didn't finish that. Let's go ahead and finish it. We'll do the whole thing here. I'll just run it this way. Let's see. So we have, well, actually, can you just read them to me? So we have John, 16 male, John yogurt. So we have the first four. We have all of Peter's. We have one of Amy's. So what's this next one for Amy? Okay, well, it'll be Amy salad.
And then the next one would be Amy 25, female, Amy yogurt.
Yep.
Amy 25, female, Jane salad.
All right. And then?
I can't really see that anymore, but it's Jane 23, female, and then whatever is above that second row on the table.
Right.
I can't really see
That would be John and yogurt.
And that would be Jane 23, female. Yeah, I can't.
Yeah, that's fine. How many columns are there here? I'm sorry, how many rows?
16.
16. Yep, exactly, just like you said. So this is the whole result of the cross multiplication. This. Okay, so there's all 16 rows. That's this yellow part. So this yellow part now is this whole relation.
Definitely feel a lot more comfortable with that now.
Okay, great. So now for the select. Right, now what does the select do? The select goes row by row, and it checks each of these, if these are true or not. So in order to keep a row, it has to pass all of those, the gender equals female, the food equals yogurt, or the food equals salad, and that the name has to equal name 2. And that's the value in the column. So for example, and now the select will go row by row. Okay, so we'll start at the first row and see if that should be kept or eliminated. So here we see that the gender is male, which is not female. So this row gets thrown out. That one's no good. Then we move on to the second row and see if we keep it. Do you want to go through this, the 16?
Yeah, sure, I'll do it.
Okay.
So you would throw out the second row all the way down until Peter because they're all male.
Yep.
And then Next, you're going to look for yogurt or salad, and everything that's left is yogurt or salad, so I don't think you throw anything out from that.
Okay.
And then you have to check that name 1 equals name 2, so that first row that's still there is not. Second one is Amy and Amy. The third one is Amy and Amy. The fourth one should be thrown out. The fifth one should be thrown out.
Okay.
The sixth one should be thrown out. And everything except the bottom row.
Yeah, very good. Okay. Yeah, so now that's the select operation. The select operation is over, and what it's kept are these 3 rows. These are the things that survived the select operation. These 3. Okay, so that's our relation right now. It has 3 rows, and what this query is asking for are the names of the females. So right now in this, let me see if I can move this down a little bit. Great. Oh no. Well, I guess I can't. Move this instead. No. Stupid. Okay. Just wanted to see the things better. Okay. So the relation that we return should only return the names. So that's what the project does. So what is the final relation look like?
Just be Amy and Jane.
Yeah, so it would be, well, actually, there's a small point here. So it'd be name text. So then the project here, let's do this. The project name, what that does is it only keeps this one column, and it throws out all of the other columns. So now it's that relation.
Doesn't matter if Amy is repeated twice.
It does, and it won't happen. And I'll explain that. Somebody else asked me a similar question, like, isn't this a problem because there'd be 2 names there? This isn't allowed to happen for 2 reasons. One, you need some key. And if your key's the name, then you can't have a repeated key. Keys have to be unique. So that's the relation way of satisfying that. The set way of satisfying that is that a set doesn't have any repeats. So the set 1, 4, 5 is equal to the set 1, 1, 5, 4, 4, 5. Right? The set is just the minimum, no repeats by convention. So the same thing, if it's a set, then that would be a repeat, and you get rid of it anyway. And so that's it. And so we have one relation with 2 rows, Amy and Jane, and that's what we said here, was what you had expected. Okay. So the select is basically the query. Kind of, if you want to think about it that way. Yeah. I mean, the select is the query on this gigantic relation that you've constructed. Can we multiply specific columns into our tables? Yes and no. The way that you could do that is you could, okay. Let's say we have this table A and B, and this has, I don't know, A, B, and C, and this has, I don't know, A, X, and Y. whatever. Then can you, for example, multiply this column by these columns? Not with a straight cross multiply. Yes, you can. The way that you would do that is you would project just A of A, and then you would project X and Y of B. And now each of these relations, I mean, this is that orange one, that is this orange one, and then you would cross multiply these. So yeah, you can do that if you want. But yeah, like there's a projection step there. Do the order of the subscripts on the sigma matter, or can they be in any order or evaluated in any order? Yeah, order doesn't matter here. Yeah, you can arrange them however you want. You can check them in any order you want. Doesn't matter. Okay, so here in this example, we cross-multiplied person and eats because we wanted to relate the names and the foods. And the person relation knows names and genders, and the foods relation knows names and foods. So each of those relations have something that we care about, and so that's why we chose them to cross-multiply and find out what all the combinations of them are. So in this third example, the reason why we have to add this, it's basically the same as the last one, except here it's checking that it has both a salad and a yogurt food. And in order to write this, that's why you need this eats here. Because otherwise, going through the select, if you just have a single column named food, then for example, trying to select here, you'd eliminate it. You'd say that that's a bad row because the food column is not equal to yogurt, and so you'd throw it out. Similarly here, you'd throw out this one because this is not salad. And there's no memory. So just because you've seen salad before doesn't mean you'll remember that you saw salad before for Amy sometime earlier when you're looking at Amy yogurt.
Professor,
Yeah.
I was just thinking that if we could, instead of having a second eats table concatenated to the combination table, if we could multiply one food column to the other one, meaning in the second eats table, when we multiply it and when we're selecting it, it would only take the rows which food, meaning food 1 equals salad, and then food 2 would equals yogurt. And it would only take those specific rows in the select function.
That could be, but yeah, then you'd have to have some projections to,
Right.
yeah, so you'd be doing some projections, you might be doing different selects. And yeah, that's sort of one tact where you're trying to kind of save a little bit of space here. Because, I don't know, yeah, there's some columns that are kind of irrelevant, I guess, to this query. So yeah, that would be maybe a way to make this one a little bit more efficient. But this is using the same kind of thinking, which is useful, but this is using the same kind of thinking as the last problem. So let me give another query here. Can I move? Yeah. I want to move everything down. Oh boy. Okay. I don't know. Is that important? But make sure it's still on the page. Fine. Okay. So this is one option. There's another option, which is, and again, this is why I think sometimes thinking about these things as sets can be useful. The females who eat both yogurt and salad. Well, we know that we can come up with a query of women who eat only, or who at least eat yogurt. So we can find these are females who eat yogurt. So you can find this set, and then you can find another set, females who eat salad, and then look at the intersection of these two sets. Because this intersection will be those women who both eat yogurt and eat salad. And so that's the second option. Just because, instead of me writing the query, how about I pick on somebody? How about Megan? Megan, we don't.
Hi, Professor.
Hey. So yeah, basically I've just written down here what I want to do. I just want to know if you can help me write the query for it.
Sure. Okay. So, I'm assuming first we'd start with writing the query for females who eat yogurt.
If you like.
Okay. So, would you have to cross multiply the person table with, sorry, I don't know what the E is called.
Oh,
Row?
row.
Is it row?
Row.
Yeah.
Yeah. You can just say R or rename, whatever.
Okay. Rename, with is it with the eats table?
Mm-hmm. Sure.
And then rename name to name 2.
Okay. Mm-hmm.
And then I think you would select, or like parentheses the whole thing, and then select gender equaling to female. And then I guess it's like and then parentheses. Oh no, wait. Who females who eat yogurt. So and food equaling to yogurt.
Mm-hmm.
And then another and name equal to name 2.
Yep.
And then parentheses around all that, and then project the names.
Okay. Very good. Okay.
Is that good so far?
Oh yeah. Yeah. Perfect.
Okay.
Yeah. 100%.
Okay. And then the females who eat salad, it's essentially the same query except food would equal salad instead of food equaling to yogurt.
Yep. Oh. Why can't I copy that? So I just want to copy it because, as you say, it's almost the identical query. Copy. Why is it doing that? Copy. There we go. Okay. Except on this one, the food is going to be salad.
And then I'm a little rough on this part, but I'm assuming that that you intersect both the queries, so it's like the upside down U. Yeah.
Yeah.
Is that it?
Yeah, that's it.
Oh, okay.
Yeah, perfect. Do you have any questions about that, or you feel comfortable with it?
I feel comfortable with it just because like I wrote down in my notes like that query from the last time that we did it. And I think I understand the queries for the most part. Or like
Okay.
the little yeah. So
Okay, very good. Yeah. Well, thanks. So, yeah, I mean, both of these queries work. You could potentially keep doing this type of tact, where you just cross multiply, and you do that many, many times. But you'll realize that the number of rows of the table grows very quickly. If you have a table of size n, where, I don't know, if you have some table A, and the size of A is n, and then you have another table B whose size is also n, then A cross B, the size of that table, the number of rows, is n squared. Which means that, and that keeps going. If you cross multiply this by B again, then that will have n cubed columns. So if you do this many, many times, then this is bad. Like, yeah, imagine 10, right? I mean, if these are, well, I don't know, let's call it length 10. Well, then multiplying 2 tables, that's length 100. Multiplying 3, that's 1,000. 4, I mean, you see how quickly it grows. For every cross multiplication you add another 0 to how long it would take. And that's in relation to whatever the original size of the table is. Probably these tables are much longer than 10 to begin with. So for small tables, that's probably okay. But for large tables, there's some benefit to keeping the cross multiplications down. I don't know if these colors help or are really annoying. You'll have to let me know. I don't know. I certainly don't want it to look like somebody barfed or something. Okay. Good. Let's see, 247, 120. Okay. Yeah. Let me first, before we move on from this query, ask if there's any questions about it. Are people comfortable? Can I explain the projection part again? Yeah. So let's see here. Let me copy this table. I'll go down here. Let's say that, I don't know, we'll take yogurt eaters. Okay? So anybody who eats yogurt, return me the names of people who eat yogurt. So this row will get eliminated from the select because these names don't match. So that will get eliminated. This row will also get eliminated because the names don't match. This row, because the names don't match. This row gets deleted because the names don't match. Here, the names don't match, so that gets deleted. Here, the names don't match, that gets deleted. Names don't match. Here, names don't match. Here, the names do match, but the food isn't yogurt. We only want yogurt eaters, so that goes away. This one's fine. It stays. The names don't match. The names don't match. The names don't match. The names don't match. And we're looking for yogurt eaters. Okay, so this is the result of cross-multiplying and renaming. There's the rename. The cross multiplication was the original table, and the select was me going through deleting the rows. So now this is the current relation. But if we return this relation, I mean, you could just return the whole thing, but oftentimes people don't want the extra information. They just want the answer to their question. In this case, it's what are the names of people who eat yogurt? And so what they want to be returned is name, that's text, is a relation that will look like this: John, Amy. And that's the relation. So the way that you get that relation from this relation is through a projection. So here, if you project and you say, I want to project and keep the name column, here you put all of the columns that you want to keep. Then what that will do is it will eliminate that column, eliminate that column, eliminate this column, and eliminate that column. And so the result is the same as that. We have the result would be this single relation with just a name column, and that's it. And that's what the query wants. What are the names of the people who eat yogurt? And that would be the answer to the query. So of option 1, yeah, we're just choosing the name. Same thing. Find the names of the females. So we do the name here. Great. Yeah, so one thing to take from this is don't forget that there's other operations. Like, yes, we've worked a lot with project and select, cross multiply and rename, but there's those other 3, intersect, set difference, and the union. Yeah, this is an example where the select can offer some benefit. Okay. Let me copy just these relations again. What just that one? Oh. Okay. So same kind of thing. This query is asking, find the restaurants that serve at least one food that John likes to eat for under $10. So, yeah, I don't know. John is hungry. He has a $10 bill, and there's a list of foods that he likes to eat, and he just wants to go. He wants to know what are the restaurants that he could go to and get something that he likes for $10. That is the query. And I'm going to give you maybe 4 minutes to work on this. And please try to actually write it down. Okay, that's a really important part of this, is trying stuff. So after 4 minutes, I'll ask if anybody has a solution, or if you think you have one, you can type it in the chat box. You don't have a price column. Here. It's in the serves relation. That's the, yeah. So this is like restaurants and their menus, right? Name of the restaurant, the food they serve, how much they charge. Yeah. So, yeah, you can write a solution if you think you have one in the chat. Otherwise, you can read it out loud after 4 minutes. But please do try to actually write something down and solve it. Okay, I'll see you in a few minutes. Okay, welcome back, guys. So, who has an answer?
I can try.
Excellent.
So we multiply the person table by the renamed frequency table, where name becomes name 2 in frequency. And then we multiply the renamed serves table,
Okay.
where restaurant is renamed to restaurant 2.
Okay.
And then from that entire thing, we select where name equals John
Mm-hmm.
and name equals name 2 and price is less than 10
Mm-hmm.
and restaurant is equal to restaurant 2.
Okay.
And then we project the restaurant.
Sure. Okay. Yeah, that's fine. Yeah, great. So let's see. That is an acceptable answer. I'd call it actually going a little further than you need to. So this would return not only the restaurants that serve food that he eats under. Oh, wait. No, I'm sorry. There's something wrong with this. Yeah. Technically, what this would return are the. Yeah, I have to reword this. This is for something slightly different. This query, or what this would return. It's a fine query. It's just not exactly what is being asked. What this query would return is find the restaurants that serve. No, find the restaurants that John frequents serve at least one food John likes. That John frequents that have food on their menu for under $10. That's what this returns. So you can, and actually you don't even need the person table here because the frequents table already has the name. But still, this makes sure that when you're checking the name here, that would be a restaurant that he frequents, and then this would just be restaurants that have a price under $10. But that doesn't say that, I mean, it would be an odd thing, but in any case, maybe John frequents places that don't serve food that he likes. And he only frequents restaurants that serve food he doesn't like. Then then there might be restaurants that do serve food that he likes, but not that he also frequents. Yeah, but most of this is good. Yes, I see. Could you use person times serves? So person and serves doesn't quite work, because person and serves, if you use this relation and this relation, then you don't know what food the people eat. You just know the names of the people. In fact, yeah, there's no way to relate these two tables together. Each of their columns are different, and in this case, you want to the relations have a relationship because there's at least one column of information that they share. So yes, here, this is good enough. Yeah, the eats table and the serves table. So instead of this, I'll do eats, and here we can do serves. And now the food is the identifying factor. So let's see, restaurant food, eat, serve. Yeah, that's fine. So you just need name equals John, food equals food 2, price is under 10, so you don't need this anymore. Is that it? John, food that he eats and foods they serve are the same, and the price is under $10. Return the restaurant. Yeah, this. Oh, sorry, this is renaming food to food 2. Okay, because we don't have a lot of time left, instead of I'll introduce the hard query, or the hard type of query that we're going to be working up to. And I'll give it to you so that way you have a few days to play with it. And the next class, we'll need to take a sort of a path where I'll have to talk some about quantitative reasoning, truth statements, and logic. And I think that is a way to systematically go from a query, go from something in English into a query. But that being said, I can still motivate the whole thing and explain what about this makes it a hard query. Okay. This. So I think at this point you're familiar enough with the 4 relations that there are. Obviously, most of these queries don't need all of them. but yeah, so the thing that makes this tricky is this word, only. So find the names of all people who frequent only restaurants serving at least one food they like. The reason why this is hard might occur to you when you're trying to come up with the query yourself. And I encourage you to actually sit down and try it, because I don't want to just give a query and say this is what all of the parts are. I'd rather have some sort of systematic way to come up with the query. Because otherwise you can sort of memorize what this query is for this exact thing, but then when you see something similar later, like you don't know how to, like, where to start. So, but the reason that this is hard is similar to the reason why finding females who eat yogurt and salad was a little tricky, because the select operation has no memory. And so the select operation, you need to have something that for a single row, you can just look at that one row and determine if this is true or not. And, you can't, the fact that you have no memory makes this tricky. It's not impossible. I mean, like, yeah, of course, there's a way to do it. But I think this is probably the hardest type of query that we'll be discussing. Are there any questions about how to understand what this query is asking? Because if you don't understand that, you can't even really think about it. I'll take the silence as a no. Okay. So then, without going into the whole thing, I'll give a preview of where we'll pick up next class, which is an introduction to quantitative reasoning. Okay, so quantitative reasoning is basically just logic. It's so quantitative reasoning is making or evaluating statements that are either true or false. Okay, so and these statements are actually called predicates. Predicates. Statements. Okay, so just like the select has a predicate, right? It's a statement that has clauses. So, for example, this, name equals John, and whatever, price less than $10, and what was it? Oh, food equals food too. Okay, and now the order that you evaluate clauses doesn't matter. All right, so let me do this actually. This whole thing is an example of a predicate. Okay, so a predicate. So a predicate is a statement, and these are called clauses. Okay, kind of like how in English you can have, well, actually just like English, you can have, sentences can, in between a word and a sentence is a clause. So each of these clauses gets evaluated as being true or false, and then the entire predicate is evaluated. So, oh, and by the way, guess that this is obvious, but here, true we'll write as 0, just for convenience, and false we'll define as, sorry, no, this way. So true is 1, false is 0. So for example, if the name is John, then that'll be a 1. And if the price is less than $10, then that's also a 1. And if the two food names match, then all of those are true, which makes the whole thing be true. Now, if the price is greater than $10, then that would be a 0. And 1 and 0 and 1 is a 0. Okay, so that's an example of a predicate. And these operations here, these are operators. Quantitative reasoning only has 3. Well, if you wanted to include an XOR, maybe 4, but I don't think we're going to be getting into XORs, although they are supported by SQL. There's the AND, which we write this way. There's the OR, we write that way. And then there's NOT, we write that way. So if you have two variables, x1 and x2, and you want to know x1 and x2, you can come up with a truth table. And this is, in this case, it's a definition. For 2 bits, where x1 and x2 are just 2 bits, they can both be zeros. x1 can be 0 and x2 can be 1. x2 can be 1, x2 can be 0, or they can both be 1. And that's it. Those are all of the different combinations of 2 bits. So the value of 0 and 0 is defined to be 0. 0 and 1 is defined to be 0. 1 and 0 defined to be 0. And 1 and 1 is defined to be 1. So the AND operator takes 2 bits. And the operation is if these 2 bits are both 1, then the answer is 1. Else, 0. The OR operation is similar, except this is true if either one is true. So here that's a 0, 1, 1, 1, and then a NOT just gets applied to a single variable, NOT x. So those are the possible values for x, and then these are the possible values for not x. Okay, so those are the operators, And then we'll have to talk about quantifiers, which are, there's two, there exists and for all. So, and that's it for quantitative reasoning. You come up with predicates using a combination of ands, ors, nots, and there exists and for all. The relational algebra and SQL, by extension, do not handle for all statements. And this is a type of a for all statement. Things kind of break down, and you need to reword the query in order to do it. But that being said, I genuinely encourage you to try to figure this relation out. Okay, guys, that's it for today's class, and I'll see you on Friday.